Hello everyone, our project provides a detailed explanation of ARIMA, seasonal ARIMA, and how to do parameter selection on these models. Let me first give an introduction to the model. The ARIMA, which is called Autoregressive Integrated Moving Average Model, has one additional parameter compared to the ARMA model, and is denoted as the ARIMA PDQ model. We learned that difference can be used to make data stationary. However, sometimes a first-order difference may not perfectly achieve stationarity. In such cases, the small d parameter in the ARIMA model represents the number of different steps required to make the data a stationary series. Let's first take a look at the mathematical definition. Once the small d parameter of ARIMA is determined, yt can be expressed as a differential equation at time t and then incorporated into the original ARMA model. You can see the formula here. Sometimes we see it in easier ones. I won't go into much detail here. Next, let me give an example of how to do prediction with ARIMA. I will use the closed price of Apple from 2019 to 2022. After loading the library and data, we can use AutoARIMA function based on the ASA method to get the parameter. And in this example, we can see the best parameter is 110. If the model's fit is not good, we can also adjust the parameters by observing the ACF and the PACF. So now we focus on how to make sure these parameters are correct. We will use box pairs approach to examine. This test is performed on the residue series. We know that a good model should have stationary data, meaning that the noise should appear randomly. The null hypothesis of this test is that the residue series is white noise. Therefore, the p-value should be significantly greater than 0.05. Let's look at the situation. P-value is higher than 0.9, so the test tells us that the model is feasible. Generally, at this point, we may not need to continue with further tests. However, if the residue series doesn't pass the test, we will need to use an alternative method, such as analyzing the ACF and the PACF to redetermine the model parameters. Next, we will focus on seasonal ARIMA. It's formed by including an additional seasonal term, and is written as follows. It involves the use of the Fourier transform as well as the partial autocorrelation coefficients. The small m represents the seasonality period. For example, in ARIMA 112129, it essentially means that the data has had a seasonality of 9, and the later 112 represents the seasonal part of the ARIMA model. Therefore, the two sets of values may be different. The process is best illustrated via an example. Here we use the sample from FPP library, which are the retail index of Europe by quarter. You can see the general information from the plot, and we can use the AutoARIMA function to do the work for us. Then we get ARIMA 0130114. When fit seasonal ARIMA, AutoARIMA function uses ns_diffs to determine the big D, which is the number of seasonal differences to use, and the n_diffs to determine the small d, which is the number of ordinary differences to use. Then we can try on forecasting on based on this model. We can see the trend on it and also 1 or 2 times the standard deviation in shadow. Also, we need to do a box pairs test to see if we can accept the parameter. The p-value is 0.95, so it passed the box test. After discussing about the two models, we should pay attention to parameter selection. We have methods like AIC or BIC and ACF or PACF to help with model order selection. And both methods have their pros and cons. Here is a brief summary that you can consider when using them. However, in fact, both methods are often used together as they excel in different areas. You can use AIC to automatically tune the parameters and then fine-tune them using ACF or PACF. Alternatively, you can change the order. So then, how can we select the parameters in AR, ARMA, and ARIMA? There is a table here. So that's our sharing. Hopefully, we can help you on basic time series prediction. This is our reference. Thank you.